In the last session, we discussed about a non-vectored interrupt, that is INTR. In this session, we'll be discussing about vectored interrupts. So among vectored interrupts, we have uh, four different types of interrupts. We have trap, RST 7.5, RST 6.5, and RST 5.5. Trap is also referred to as RST 4.5 at you will see RST4 trap being referred to as RST 4.5. Fine. So the starting address of ISR in these cases is pre-specified. Starting address of ISR, where ISR is the interrupt service routine. That's actually a subroutine used for servicing of interrupts. So this address is pre-specified. It will not change as in case of INTR. The address is not pre-specified. We can have different address for the instructions. Uh, Pre-specified and fixed. So we have four different types of vectored interrupts here. One, we have trap, that is also, as I said to you, referred to as RST 4.5. Then we have RST 7.5, RST 6.5, and RST 5.5. So the address of the interrupt services of these are, for this case it is 8 cross, that's 8 into 4.5 in hexadecimal numbers. That actually comes out to be 0024 hexadecimal. Then for RST 7.5 it is 8 into 7.5. That comes out to be 003CH. 8 referring to the 8-bit of 8-bit microprocessor. Then 8 into 6.5. So starting address of this is the ISR of address of ISR of this is 0034, and then you have 8 into 5.5, that comes out to be equal to 002CH. Fine. So these are the addresses of the subroot of these the microprocessor 8085. You have four different vector interrupts, and these are the addresses of their ISRs. So these memory locations are actually not accessible to the user, and they are actually reserved for the monitoring of the memory location. So that's why I have been saying to you that there will be certain memory locations from 0000 to FFFF. There will be some locations that are actually specified in the 8085 microprocessor for certain purposes, and you can see these memory locations are specified. These are used for the vectored interrupts. Now talking about among these about the trap uh, interrupt. Now as far as the trap interrupt goes, it is a non-vectored interrupt. It's a vectored interrupt, sorry, and it has the highest priority. As I said to you, it is the highest priority interrupt. So among all the, if all the interrupts, if the IO devices are interrupting the normal flow of the normal process of 8085 microprocessor, and all of them are actually being triggered. Among them, trap will take the highest priority and it will be executed first of all. And also, it is a non-maskable interrupt that we have already specified. It's a non-maskable interrupt. That means we cannot disable or enable this interrupt, it will always take precedence over whatever program is being run at a certain moment. Fine. So it cannot be ignored by the microprocessor in any case. So what is this trap used for? There will be certain applications where there might have to be there is going to be certain priority has to be set that the microprocessor cannot be ignoring these situations. So used in handling emergency situations. So what can these emergency situations be like? Like triggering of the fire alarm, or an emergency shutdown, or can be uh, calling an ambulance. Fine, calling 911. So these will be in emergency situations where we cannot actually ignore the application, and for whatever application they are used, they have to be have such priorities that they cannot be ignored by the microprocessor. Fine, and it's a vector interrupt that we have already specified, so it need not be enabled or need not be enabled or need not be disabled, need not be enabled and cannot be disabled. So as far as this interrupt goes, it's edge sensitive and level sensitive. That means uh, it will make a transition from low to high state and stay in the high state till recognized by the microprocessor. Fine. So it has to make a transition from low to high and will remain in high until the microprocessor basically uh, uh, basically is able to recognize the interrupt. Fine. So this is your edge and this is your level. Then we have the three interrupts: RST 7.5, RST 6.5, and RST 5.5. So regarding these three interrupts, they are again vectored interrupts that we have already discussed, and we have also discussed whether they are maskable interrupts. That means we can enable them or disable them, and they therefore need to be enabled and can be disabled. Just like the INTR interrupt, they need to be enabled and they can be disabled. In order to use the interrupt, we again need to use the EI instruction, enable interrupt instruction, that needs to be included in the program. Just writing EI is not actually sufficient for unmasking these interrupts, but as against INTR instruction, EI will not be sufficient. There will be another instruction that needs to follow up the EI instruction. Fine. So EI instruction is required to enable them, but not sufficient for unmasking. So what we have to use another instruction, and that is sim instruction that needs to be used for unmasking these interrupts. So we have discussed actually two instructions before this, EI and DI. So they form a part of the machine control group, and we have another instruction We have SIM. So this is yet another instruction in the machine control group. Fine. So SIM, you have to write SIM. So regarding this SIM, it's actually set interrupt mask. So these are actually used for these three interrupts for masking and unmasking, and also for serial output of data. So they actually serve two purposes. Uh, they are used for SIM, that is set interrupt mask, for unmasking and masking and unmasking of these three interrupts, that's RST 7.5, 6.5 and RST 5.5, and also for serial output of data. So used for what purposes? It's actually used for masking and unmasking of RST 7.5, 6.5 and 5.5, and secondly for serial output of data. So what we do here is, before actually we use the same instruction, we will have to load the data byte into the accumulator. And if this is our accumulator, you have SOD, you have SOE, you have X, you have RST 7.5, you have MSC. So if this is a accumulator, what we have to do is we'll actually be transporting the data byte into the accumulator, and this will be from least significant bit to the most significant bit. All of them will be used for certain purposes, and you have these two will be used for serial output of data. If SOE is 1, it means enable the port. Fine. X means don't care condition, it's not required. All of these three, they are actually used for interrupts. So this SIM, before transferring the data to SIM, we need to load the accumulator with the data byte, and from accumulator to actually go into the SIM, this register. This register will have 8 bits, and all of them will have certain values, certain they will have certain work to do. The first two most significant bits are used for serial operation. The last 5 bits, they are used for interrupts. And if MSC is 0, that that means in that case all of these 4 are actually ignored. If MSC is 0, all of these 8 M 5.5, 6.5, M 7.5, they are ignored. A0, this is A0, this is A1, this is A2, A3, A4, A5, A6, A7. So A0 to A2 are ignored. If MSE is equal to 1, mask is set. So now we can use these 3 bits for certain operations. So if these, we can have these 3 values either 0 or they can be 1. 0 simply means they are unmasked, and 1 means they are masked. So you can unmask or mask M RST 7.5, 6.5 and 5.5. The M, if it is M 5.5, that's if A0 is equal to 1, that means mask RST 5.5. If A1 is equal to 1, that means M 6.5 we are talking about. If it is equal to 1, then that means mask RST 6.5. If M 7.5 is equal to 1, that's actually A2 is 1, then mask RST 7.5. MSC here means refers to mask set enable, so it can either be 0 or 1. So it will actually disable or enable A0 to A2 pins, A0 to A2 bits. RST 7.5, that is actually A4 data. This is not a RST 7.5, sorry. This is R7.5. R7.5 simply means reset RST 7.5. So it's an additional control that's used for RST 7.5. We could have reset RST 7.5 using A2 also, but since this has the highest priority next to trap, so it has an additional control feature. So if it is 1, if A4 is 1, RST 7.5 is reset regardless of A3 and A2 status. If R7.5 is equal to 0, RST 7.5 can be used depending upon A3 and A2 values. Fine. RST 7.5, if it is 1, if A4 is equal to 1, RST 7.5 will be reset regardless of the value of A2 and A3. If RST 7.5, that's A4, is equal to 0, RST 7.5 can be used, but depending upon the status of A2 and A3. While as SOE, they are used for serial port enable and serial port disable. If SOE is equal to 1, it will enable the port. If it is equal to 0, it will disable the port. This is actually the macro RTL of this instruction. SOD will actually, then your A7, that's the most senior bit, will carry the actual data that needs to be serially communicated. You can actually transmit the data 1 bit at a time. So you need to only have 1 bit to transmit for serial communication, and that is this data byte. This is actually data simply that will be transmitted serially transmitted data. So this is the register, and can be used while the sim instruction is being used through the accumulator, and these 8 bits of data, they have certain significance if they are 0 or if they are 1. Fine. So this is about the interrupts, how we can enable or disable the various types of interrupts, and which of them is maskable, which of them is not maskable. As far as RST 7.5 goes, it's again edge sensitive. RST 7.5 is edge sensitive. RST 6.5 and RST 5.5, they are level sensitive. While as we discussed trap before this, it's both level as well as edge sensitive, so that it actually remains high as well as it has to transit from low to high transition. So this is all about interrupts, how we can enable them using different instructions in the machine control group, EI, DI, and using the sim instruction. and how the five interrupts have different priorities, which of them is maskable, which of them is not maskable, which of them is vectored, which of them is non-vectored, and how they can interrupt the normal processing of the data. So we are actually discussing I/O interfacing. We have discussed the simple I/O, we have discussed the pooled I/O, and we have discussed the interrupt I/O. We are actually now left with DMA, that's direct memory access, that we will be doing in the next lecture.